Hello friends, today we'll talk about microcontrollers. This is one of my favorite topics and I hope you'll understand this topic from the very scratch. For this particular video, I would understand that you know something about digital electronics, AND gates, OR gate, flip-flops, counters, etc. So let me introduce you to some of the components of digital electronics. You must be knowing about gates, either they come in AND, OR, NOT, XOR, etc. They are flip-flops also, JK flip-flop, RS flip-flops. There are counters like mod 10 counters, mod N counters. Memories, I expect you to know something about RAM and something about ROM. Communication, we have parallel in serial output, serial in parallel output, or basically serial communications. So all this is a prerequisite for understanding microcontrollers. Let's take for example, we want to build a mod 7 counter. This is a problem statement and this is the design flow. So we first design it on pen and paper. We'll require a clock, some flip-flops, some decoders and a reset circuit. And then after we design it on pen and paper, we select the ICs from which we can make these few components. And after that, we use a breadboard and a few wires to interconnect these ICs. And we will be having a few LEDs as an output, and then we test this circuit. Now let's see what happens if something goes wrong in the output. What we do next is to go back to this stage again. So if something went wrong with the selection of the ICs or circuits, then we have to again disassemble the old circuit and assemble new ICs and interconnect different wires and then test it again. So this process keeps on repeating again and again, which may be cumbersome for large or complicated circuits. Now let us change the scenario. Where there was a few ICs which we assembled, now we have a box. This box contains AND gates, OR gates, flip-flops, and maybe some counters. So this box is physically an IC, but this time there's a change. We can now program it or burn it. So now when we design, then we program this box and then we test it. Now if something goes wrong with our testing, then we again go back to design and then program again. The advantage out here is that there is no need to physically assemble the particular ICs or wires on the breadboard. Here we just need to change the program. This has given rise to the birth of the programmable logic controller. It is called a PLD or a PAL or a GAL or a CPLD, a complex PLD. Now the concept was changed. So we had a program which could program the PLD and the output would have come directly from the PLD itself. So there was a concept of a software where instructions were given. Now the flexibility of software you know, because everyone is accustomed to software. Anything can be changed and saved, modified very easily. Now PLDs or programmable logic controllers had a very limited amount of gates, etc. So it was used to implement very simple circuits. And as time went by, we were wanting a particular device which could take instructions and also decision making and give an output accordingly. So slight change in design, we had this microprocessor which had a CPU, a think box, and an ALU, basically a math box, and some RAM. Now we would put this program inside the PROM or a programmable ROM, and this particular ROM is to instruct this microprocessor to give a certain output. So this was the logic. But as time went by, even the microprocessor wanted a few other things. Like in a computer, we have input and output devices. So we have a keyboard, we have a display, we have a network connection, and many other such devices which are connected to the computer, which you can already see in your home or office. So as the microcontroller was evolving, we wanted a lot of things packaged into one box. That was basically, we had a microprocessor in the middle of the box. We wanted some RAM where we could do a math, keep some temporary data. We wanted some ROM where we could keep some fixed data. We wanted some input and output because we wanted to control something, we wanted to take some inputs. We could have some analog outputs or inputs, so we need a analog input device which is called an A to D converter, analog to digital converter. We needed a DAC, a digital to analog converter. We needed some timers or counters. We needed some communication like serial communication. We needed some, say, PWM for motor control, etc. So, and of course there's something called interrupts, which is a very interesting topic. So we needed some interrupts to our program. So all these were connected to the MPU. And one more thing I should not forget was a clock. A clock is like a heartbeat to the microcontroller. Without the clock, the microcontroller will not work. Now, if I put them into a box, this is called a microcontroller. And that is the difference between a microprocessor and a microcontroller. A microcontroller is a box of paranoia. You must be knowing a few names, of course the Arduino, where people are very accustomed to this particular thing. The basic ones were Intel 8031 architecture microcontroller from Intel. the PIC microcontroller from Microchip. The Raspberry Pi is also a very famous microcontroller. And all these microcontrollers are coming into shape nowadays for a lot of things in the environment. So friends, microcontrollers can be found in everything that is moving around us, like washing machines, TVs, recording equipment, etc. So it is very important that we understand how they work. It is basically something which is embedded into your system. Embedded system starts from this. So thank you for watching this video. We'll come up with more detailed videos on microcontrollers in the time to come. Thank you for watching.